Hello, everyone, and welcome to Talk Nerdy. Today is Monday, June 29th, 2026, and I'm the host of the show, Dr. Cara Santa Maria. And I do want to apologize for not putting out a new episode last week. It has been just a hell of a time over here. In addition to, if you listen to the Skeptic's Guide to the Universe, the other show that I work on, you may have heard that in addition to something as innocuous as having an endoscopy, colonoscopy in the middle of the week that threw things off, to such large concerns as Evan Bernstein's resignation from the SGU. And I would turn you to the most recent episode of SGU to learn more about that, all the way to the tragic news that we recently received at my work in the hospital of the death of my direct supervisor. It's been a trying week, and unfortunately, I just wasn't able to make it to air last week. So I appreciate your patience, and I'm glad that you're sticking with me, because this week we've got a really good one for you. But before we do dive into this week's episode, as always, I want to thank those of you who make Talk Nerdy possible. Remember, this show is and will always be 100% free to download. And the way we can offset that fee, basically provide this free service, especially for all those who either can't afford or just, can't prioritize paying for podcasts in their life, it's that individuals like you are offsetting that cost. The way we do it is using the Patreon model, which means you pledge your support on an episodic basis. And so right now, I just want to thank my top patrons this week. They include Chuck Blell, David J. E. Smith, Daniel Lang, Mary Neva, Will Dufresne, David Compton, Brian Holden, Gabo J., Ulrika Hagman, Pasquale Gelati, Rika Maharaj, and Joe Wilkinson. Thank you all. And if you're interested in pledging your support, all you've got to do is visit patreon.com/talknerdy to learn more. All right. This week, I had the opportunity to chat with Roxanne Khamsi. She is an author and a science communicator. She's written for a ton of outlets that you read: New York Times, The Economist, Popular Science, Scientific American, Slate, Nat Geo, on and on and on. She is a contributing writer for The Atlantic currently, and historically, she served as chief news editor at Nature Medicine, which is, a huge research journal. She did that for over a decade, and before that, she was a reporter for New Scientist magazine, which is also a widely circulating UK-based science magazine. She also has taught at Stony Brook University in Long Island through the Alan Alda Center for Communicating Science and at the Craig Newmark Graduate School of Journalism at the City University, New York. And she served on the editorial advisory board of TED Med. She has a new book. She has her first book. So this is very, very exciting. It's called Beyond Inheritance: Our Ever-Mutating Cells and a New Understanding of Health. So without any further ado, here she is, Roxanne Khamsi. Well, Roxanne, thank you so much for joining me today.
Thank you, Cara. It's great to be here.
I always love to talk to a veteran science journalist, especially one who writes a full-length book, because I don't know. I struggle, man. I don't know how you do it. It's so much work. Does it come easy for you, or was it like a real slog?
I always wanted to write a book. That was one of my goals when I was growing up. So I think part of it, I think, like, as you get older, you realize how, and I've been doing science journalism for 2 decades, so I feel like I can kind of say something with that kind of statement. But I do feel that you understand how much just wanting to do something and feeling like the idea comes to you and you have to really run with it. Is a large part of what keeps you going through it. And I was really curious what it would be like, because this was a topic that I felt I couldn't do in just a magazine feature. This idea in this book is about how our DNA changes every single day of our lives. And there were a bunch of different scientists from different fields that were coming to the same conclusion, but just like really not talking to one another, not understanding how this idea has been percolating throughout decades of history. So I felt like there's no way to do that in 5,000 words or 10,000 words. It's really an idea you want to sit with and like peel apart like an onion.
Yeah, and for some journalists who are writing long form, when they finally write the book, they're like, oh, I had this one piece, or I wrote multiple pieces and I was able to kind of synthesize but add to it. Have you nibbled around the edges of this in any of your publications in magazines, or is
Yeah,
this the first time
absolutely.
you've even? Oh,
No, no,
okay,
no.
okay, okay.
So I went to Florida in 2017, and I got this tip from a scientist that there was like this interesting stuff going on in the field of cancer where, they're basically getting the idea that like it's not just one or two mutations that causes a cancer to form in your body. It's a whole bunch, and then there's like sometimes even like what's called a big bang of mutations in the cancer. So there's like thousands of mutations in one person's tumor. And then there were these scientists at the Moffitt in Tampa, Florida, and they were trying to understand how they could like play cancer cells against one another by removing and restarting therapy at like specific intervals. So like they'd take away the drugs they were giving these patients with prostate cancer and like let the drug sensitive cells like grow faster than the drug resistant cells. And then they'd hit the cancer with the treatment and like be able to knock out more of it using that approach. So just kind of just the way in the wilderness, like certain animals compete against one another for like resources. They were taking that idea and applying it to the the cancers to help this essentially the cancer cells with the less worse mutations take over.
And so how did you even start thinking about that? Like how did you even get to the place where this was on your mind?
Oh, well, yeah. So I didn't finish that thought really. So like that was from a tip from a scientist who was like, hey, like cancer biologists are really taking this idea of like evolution in the body like is happening and we can leverage it.
Mm.
But then when I came back, I was like looking at research papers for another part of my job. At the time, I was in addition to like writing for Wired, where I published that story, and the New York Times Magazine as like a freelance journalist. I had a day job as an editor at a research journal called Nature Medicine. And I was like doing a news roundup, and I found this paper that was talking about how mutant blood cells, so cells that are acquired mutations in the blood, were linked to an increased risk of heart disease and stroke. And I was like, well,
Mm.
that's different from cancer. Like I knew that we could acquire mutations as we grow older, but I didn't know that that caused more than cancer. And then I just like dug around and I found out, okay, well, it's not just like cancer. It's not just heart disease. It's also like epilepsy. It's like Alzheimer's. It's liver conditions, like all sorts of mutations can pile up in the body. And ultimately, it's probably the main driver of aging, or potentially a large driver of aging, just the idea that we rack up errors in our DNA over time and they stay in our cells because it's easy to get a mutation, but it's hard to like erase it. So I saw all these threads coming together and I was like, okay, like I got to pitch this as a book. And I wrote it and I recorded the audiobook, and I feel like I needed to spend time with it and to really dig into the historical archives and find how this idea has just like been like over a century in the making, and why we're going to be talking about it so much more in the future.
Well, and also just why not many people are talking about it. I mean, even as
Yeah.
you're introducing this concept, and my bias is that I now work as a psychologist in a cancer center, in addition to doing, the public science communication that I continue to do. I can't help but think, okay, what you were describing, like, gosh, how do I even phrase this question? With regards to other disease states, how do we define cancer then, right?
Well, I mean, yeah,
Like,
yeah. Well, I mean, that's the thing. It's like a lot of the scientists, when they talk about mutant cells, they have to kind of preface it by saying, okay, these are um, non-malignant, but like
right.
they're non-cancerous cells, but they are mutant cells in the body. And it's interesting because you talk about um, cancer patients and psychology, and there you're talking about, obviously with cancer, there's mutant cells that drive like that, like growth, and
Hmm.
also oftentimes the resistance to the chemotherapy and all the treatments.
Yeah, and the recruiting of
Um,
blood vessels, and yeah, all
yeah,
the
yeah, there's a
horrible
lot.
things they
Yeah,
do.
these cells are like rewiring themselves essentially. But then
Hmm.
on top of that, it's interesting because then you're also talking about psychology in the brain. And,
Mm.
there is that sense of DNA change we know that happens in our bodies that causes cancer. But like you're saying, like a lot of people haven't yet really fully understood that even the healthy, quote unquote, healthy cells in our bodies, in our brains, for example, we're picking up trillions of mutations every day. Like by the time a person is 100 years old, they've looked at centenarians and they've taken cells from their blood and they found that, there's around 3,000 mutations in a given cell that aren't all in the other parts of the body. So, we're just kind of, every day our cells through wear and tear break, their DNA breaks, and like we have DNA repair enzymes, but they don't always do a perfect job. I like to say they're human too, right? So
Yeah.
so if a mistake's made in the patching up, it just carries to all the daughter cells. So yeah, I do think that this is something important for people to understand, not just on a metaphysical, like, meaning of the universe thing where like you and I are having this conversation and our brain cells are mutating even as we're talking, but also to understand like what it does mean for cancer treatment, what it does mean for the diagnosis of diseases like heart disease and our risk factors for these things. So I'm kind of on a mission for people to get the idea that our biology is just like much more dynamic than they might have traditionally thought.
Yeah. And so I feel like there's so many different ways to approach this. I think just as questions pop into my head, I'm going to approach it in the most non-linear way possible and see if anyone can follow. But one of the questions that comes up right at the top is maybe we can talk a little bit about like, what is a mutation? What happens in our body when our genetic material does mutate? And like, what are some of the checks and balances? Because obviously you mentioned before, like when there are times where the error correction doesn't work or where the load is too high, it may be passed on. But there are plenty of times where, mutations are happening all the time and our cells are really good at correcting that, right?
Yeah, absolutely. Yeah, well, they're good at correcting certain, like, so mutations kind of, I mean, if a scientist might consider a distinction between DNA damage and mutation, I
Mm,
don't, because I think that ultimately the lay people kind of understand them as the same thing. So
mm,
to a scientist's mind, a mutation is usually when like there are, let's just back up for a second. Our DNA in each of our cells is comprised of these essentially letters, like scientists will call them nucleotides, but
mm.
they're ACTG for our all intents and purposes here. And there's 3 billion, if you lined up all the DNA in a given cell of yours, there'd be like 3 billion of a string of like 3 billion letters if you lined it all up together. And so imagine having to copy that every time you make a new cell, right? They copy the
Right.
DNA into the new cell. If I gave you a book with 3 billion letters and I was like, Kara, like, write this all down with a pen. I mean, I trust in you very deeply, but I also think you, like me, would probably accidentally, like if it was like ATTCG, like maybe you'd say ATT, I don't know, GCCC, I don't know. Like, like there's,
Yeah, like I'd switch some or some would get left out or I might add
yeah,
a line somewhere on accident.
and I shouldn't put it all on you. Let's talk about if I were to do this. I would make these mistakes, right? So even in just the and like, we have so much cell turnover. So a
Mm,
mutation in this sense would be like if we did make, if you are or me, one of us made, or you or I made like an error in the copying, that would be considered a mutation. Because when the next cell would like go on to like read that instruction booklet, right, of DNA to make the proteins it needs to process, I don't know, sugar or like, um, I don't know, like run some kind of operation in the cell, it
mhm.
would it would kind of go to that gene and all of a sudden be like, wait a second, like this gene, this isn't working because there's an error. So that's when you get in trouble with mutations. That they can happen in parts of the DNA that like don't have an effect, right? Or that cell might die, in which case, no biggie.
Mm.
But it might happen somewhere where it does matter.
And so oftentimes when it does happen, because like it's going to happen because that's just the nature of being alive, there are like mechanisms in place to like find it and either, like you mentioned, kill that cell so that it doesn't wreak havoc or do some type of correction so that there's not a big downstream effect. But
There are like error correction mechanisms in the cell, but it kind of works better where there's like a big mistake the cell can spot. When it's
mm,
something where like there's a single letter change, and again, that's kind of where we're talking about DNA breaks, which the cell is like it's easier for them to recognize. But if it's just like one letter's wrong, I mean, again, going back to the book, it's like, imagine if I like forgot, like if there's like a paragraph and I pressed return in the middle of the paragraph, your eyes could like spot that.
Yeah.
But if I change like H to C in a word, like hat to cat, like you might be like less able to catch that mistake. And yet a single letter change like that can have huge effects. Like there are many, many, many inherited disorders, for example, where somebody's life is just truncated because of a single letter that's wrong. And it's one of the injustices, I think, of our biology is that like it's so fragile in some ways.
Yeah. And so there's these examples, like you mentioned, where there are mistakes, mutations, damage to DNA that get passed down generation to generation, especially in situations where maybe the symptoms don't come until later in life after somebody's already had kids, or situations where you only have like a 1 in 4 chance of getting that. They tend to continue throughout the population. But there are other examples, as you mentioned before, where your own DNA is damaged throughout the lifespan due to mutagens, carcinogens, things like that. And then disease states can occur within a single lifespan as well, right?
Yeah, so part of my mission is to kind of reframe even how we hear the words genetic disease. Like, I bet you and me, if we had this conversation 10 years ago and we said genetic disease, we would automatically think inherited disease,
Oh,
inherited.
I still do. I definitely think
Let
heredity
me
when you
change that.
say, yeah,
Let me
genetic
change that
disease.
for you
Okay,
today.
all right.
So, we think about things like cystic fibrosis, where a severely tragic disease where there's like, like a mutation that will disturb how cells kind of their channels work to move stuff around. And what happens ultimately, it affects different organs, but the lungs are primarily affected where you are just more prone to these infections that you and I would not need to worry about, assuming you don't have CF. Like, um, a little asterisk there, which is like there's these new drugs that have come that have completely changed the disease, so that 90% of people with CF now have this great solution where essentially they can correct the gene function. But
Wow.
let's think about, that's an exception. A lot of these diseases don't yet have these easy to take medications. I'm getting a little sidetracked, but just to say that like CF, sickle cell disease, muscular dystrophy, people have probably heard some of these names, Tay-Sachs, PKU, like all these different inherited disorders where maybe like there's a metabolic error. They're generally things that have been passed generations, right? CF is traced back thousands of years to cystic fibrosis is traced back thousands of years to Europe. Some of the mutations, right? For
Yeah,
that,
and you mentioned Tay-Sachs. Like
yeah,
anybody who has done a DNA test and knows that they are predominantly Ashkenazi inherited in their heritage, and is partnering with somebody who's Ashkenazi, they'll often do a lot of genetic counseling before even deciding to have children,
right, yeah.
because there are genetic diseases that are so prevalent within that population.
And these are just, like you say, like you can look in the family tree and you can just find a bunch of people affected by these because they are passed down. Um, now, genetic disease is not always inherited. Like you alluded to in my book, I talk about how it can happen at any point. Like any time after, for example, like the sperm and the egg that made you came together, and there's a lot of cell division that happens at the embryo development stage. I'm kind of laughing as I'm saying this because um, I have a son, and when I was pregnant with him, I kept, all women who are pregnant just get so thirsty. We're like drinking water all the time. And it's partly because like there's a lot of cell division that's happening in you. It's like very energetically intensive. It's very rapid. And I say this because like imagine I was like, Kara, here, like take this book and copy it like letter for letter. And you have, let's say it's a 200-page book and I give you 6 months. Okay. That's like basically the cell turnover of an adult. let's approximate. But then if I said, I'm going to give you 2 days to do it, that's kind of what's going on when it's early embryonic development. Things just happen faster. The copying happens faster. And so I think, there's a lot of errors that can happen, and they do. And so genetic disease can happen when embryonic cells acquire a mistake because the DNA was there was a mistake in the replication. Or it can happen, here when you and I are sitting, we might have a mutation that crops up in us that is pathogenic, could cause cancer, or it could cause good things. I mean, my book also talks about how we rely on mutation to survive. And as we get older, 1 or 2 out of every, I always get this number, I want to get this right. It's 1 out of every 5 or 1 out of every 10 people 70 years or older has a threshold level of these mutant blood cells that have kind of just happened to accumulate over their lifespan that can double their risk of heart disease or double their risk of stroke. So it's common. It's common. Men don't know it, but by the time men are in their 70s, 40 to 50% of them have a substantial number of their blood cells missing the Y chromosome, or cells in their blood, I should say, because red blood cells don't have a nucleus, but other cells, white blood cells, they just tend to lose their Y chromosome as they get older.
It's already so small. It's not a lot there to lose compared to the X, that's for sure.
I'm not going to cry too many tears about this, and it's interesting because people are so what? Well, loss of Y, and also, by the way, there is loss of X too, because women have 2 X chromosomes, and they do tend to lose an X chromosome as we get older, but it's less, because we have a backup, it's thought to be less intensive, but we just don't know as much because, of course, they haven't studied women as much as they studied men.
Of course.
Shocker. But the loss of Y, which has been better studied, is linked to a whole host, risk of Alzheimer's is up, risk of cancer is up. But the thing is, it's not clear whether it's causal. There might be something upstream that's causing both loss of Y and the risk of these other things. So, a lot of stuff happens as we age, with our DNA.
Yeah, and our risk factors for most diseases increase as we age. But probably this is just absolute conjecture, but probably the diseases that we have best linked to DNA damage and mutagens have a higher kind of increase in risk the older that we get.
Well, the thing is that they've actually started linking these increased DNA change, the increase in mutation, to the diseases of aging, right? So it's not just that you have a higher risk of mutant cells linked to a higher risk of heart disease. They've now shown with mouse studies and cell studies in the lab that those mutant cells are able to induce more inflammation or respond with a more inflammatory response, probably because of the mutation that they've acquired. It's often in certain genes like TET2. And so heart disease is a disease of inflammation, atherosclerosis. That's when blood vessels, it's an inflammatory disease. So the idea is the DNA change has gone haywire, kind of boosts the inflammation in your body that then precipitates these diseases of aging. It's kind of it's somewhat speculative. I know you come from a data perspective, a skeptic perspective. So I'm careful here in saying none of this is definitive, but the evidence increasingly looks like there are connections here.
I mean, it does kind of make sense, even though it is a pretty intense, I guess, paradigm shift for a lot of people to move into. But and maybe it's because I don't have very specialized knowledge in these areas. I could see people who are the most specialized being the most resistant sometimes to changing their gestalt thinking. But, anybody who has been studying aging, anybody who has been studying the relationship between these different diseases of aging has probably noticed mutagens or mutations, damage to DNA across the spectrum in the lab, but it's probably been kind of hard to put their finger on the relationship, right?
Yeah,
Is it that the older we get, the more our DNA damages, and that causes these diseases? Or do these diseases cause downstream damage to our DNA? It's probably hard to know.
I mean, there's definitely that question, but because they can do some of this stuff in like mouse models now, and they can do functional assays, they can do tests that kind of show how to connect the dots. And also because there are people that are at the extremes of this. So like I write in the book about Werner syndrome. And so I mentioned a particular case where I spoke to the son of Michael Prescott. And Michael Prescott, he's a fantastic individual. I never got a chance to speak with him directly, but his son told me how so Michael Prescott got his first heart attack in his 30s. I think it was on his son's like 4th birthday, maybe. I can't recall. It was on one of his son's birthdays. Yeah, in his 30s. And then he had like 4 other heart attacks in the same year. And then like all these health things started. He started getting cataracts, like his hair went gray. His son has said that by the time he was in his early 40s taking him to like baseball games, everybody assumed that Michael was his son's grandfather. He looked like in his 60s. And his doctors I think were at Vanderbilt, like not like it was a great institution, not like a small town.
Like rural, yeah.
Rural, yeah. Not nothing against any small town hospital, but they couldn't figure it out. And so he would sit in this recliner in like the evenings in the living room, just like reading research papers. I'm sure it'd be different now. Like you'd probably ask ChatGPT and have an answer in 2 minutes, but he had to look through the research literature at the time. And he ultimately went to his doctors and he said, I think I have this thing. And they tested him and they're like, you're so right. Like this explains everything. And what he had was Werner syndrome, where essentially you age super rapidly. Unfortunately, he died in his mid-50s, which is exactly what happens in most cases. And what happens in Werner syndrome is you have just like a rapid accumulation of mutation. So there's all this evidence piling up that mutation and aging is linked. I also talk in the book about like zoo animals that have been like examined, and like they looked at giraffes, everything from giraffes to zebras, and then also like mouse and cat and dog, like human tissue. And they found that like when animals live to their lives, like maximal lifespan, it seems that like no matter how short or long they live, they end up with like 3,000 mutations in their gut cells. So the idea is that like the animals, like the mouse that lives shorter, just mutate faster, and the ones that mutate slower live longer. So the math, I think, as the young people say, or the math. Did I use that right? You think?
I think so. Don't ask me. I'm not a young person. It sounds good to me. But it does kind of beg an interesting question that I've always wondered, and I don't know if there is an answer to this question. But let's say we're talking about something as, I don't want to say as straightforward as cancer. Cancer is in no way straightforward, but where the relationship between mutation and DNA damage and cancer diagnostics and symptomatology is I guess fleshed out pretty well. I've always wondered, is it a threshold response? Like, is it that, because we know that there are people who have mutations to their DNA before they're ever born, like they have disrupted oncogenes or tumor suppressor genes that will cause it to be easier for them to get cancer. It's why there's such a thing as childhood cancer. And then we know that there are people who are exposed to intense, mutagens, like astronauts, or people who smoke cigarettes their entire life, or, people who are exposed to environmental toxins, who are just like experiencing large scale damage to their DNA. But of course, we've all heard the story of the woman who smoked her entire life and never got cancer. And we've all heard the stories of people who were just like so unlucky. Is it about the load? Is it about all of the, I mean, like, there must be an algorithm out there.
For the Rolling Stones. Why is my mind blanking? I read his autobiography and it was amazing. This is embarrassing too.
Oh, I have to Google that. So don't worry about that. Mick Jagger. Duh.
Yeah,
Mick Jagger or Keith Richards?
No.
Mick Jagger.
Keith Richards.
Okay.
Amazing autobiography. Like, wow, what a book. If
Mhm.
people don't want to read my book, they should read that book too. So, I mean, how is he like? He's like the epitome, right, of like living a hard life, and he seems to be doing great, right?
Right,
Um,
right.
and so, drugs and rock and roll did pretty fine by him. So, um, yeah, I mean, it's funny because I'm also working on a piece right now for The Atlantic about how people with like mutations that should be fatal are still alive. Like there is some
Mhm.
question that hangs about this. It's interesting they mentioned astronauts, by the way, because in my book I talk about how astronauts actually do have more mutant blood cells than the average person or the average person of their age.
Well,
So
yeah, they're like not shielded up there, right? They're getting hit. I mean,
yeah,
even flying in a plane is not great, and they're like extra flying.
maybe I
They're
should tell
far.
Elon Musk. Maybe that would be a way to get him to stop
Right.
thinking about living on Mars.
No,
Um,
let's just get him to go
well,
to Mars. He can
exactly.
be the guy. Yeah,
Also that,
I'll be
also
fine
that,
with that.
totally that too.
But yeah, I have always wondered, is there a threshold? Is there an unwritten threshold? And maybe it's different for different people where, they cross into the Rubicon and all of a sudden, okay, now it's Alzheimer's, now it's cancer, now it's these other things. But up
Well,
until then,
you
it's
know,
not.
it's a really profound question. It's like a very deep question. So I think that
Mm,
let's like pause and appreciate how how important it is because even people, for example, that I said 1 to 2 out of every 10 people in their 70s have these specific kind of like mutant cells in their blood that are linked to heart disease and linked to cancer, but not everybody is getting heart disease and cancer that has these mutant blood cells. I think maybe scientists might suggest that like there is a certain amount of vigilance in like from the immune system about like clearing out cells that seem to be bad actors. I don't know if that's
mm,
the reason why. I mean, some of
hmm.
it just could be bad luck, good luck. Um,
Yeah.
luck is kind of a tricky term in biology, right? Because there's always something determining it. Like there's some mechanism, but it just might be so small scale that we'll never really find out. Um,
Yeah.
but like on the larger scale of things, I know I personally, after having written this book, have changed some behaviors just because it's it's kind of like at the end of the day, you might not be able to determine your health, but you can stack the odds more in your favor. So sleep is extreme. It's like seems to be very well established to like lower the prevalence or risk of mutant cells in your blood or mutants. And of course, I keep talking about the blood because it's easy to sample. Like it's kind of hard to
Ah,
talk
right.
about.
Because that's what you're going to see in research studies. Yeah.
Right. Yeah. I mean, I don't want someone coming to take my brains. Like, I got my thyroid level checked. They took my arm and took my blood. Like, I don't really want them to take my brain cells. Who knows how many I have left? So,
Oh, yeah. I was just talking to my neurologist about that the other day. Like I take Prozac and it works really well for me, but I also have this like weird neurological sleep disorder called IH. And I have to
okay.
take these crazy meds so that I like am awake enough during the day. It's like similar to type 2 narcolepsy.
Oh,
And I
wow.
was talking about how once these orexin drugs, this is so
Yeah, I
like
know about
neither here
orexin
nor
drugs.
there, but yay.
Yeah.
Okay. So anybody listening, this may apply. If not, don't worry. Just I'll be past this in a second. But once these new orexin drugs are on the market, I'll be so curious to see how well I respond to them because ultimately it's anybody's guess why I have IH. Is it that I don't make enough orexin? Is there something wrong with my GABA? The only way to know is for
Yeah.
somebody to do like a spinal tap. And I'm like, not
Right.
worth it.
I mean, I do see
It
a
is.
future where
Mhm.
you'd be able to get better diagnostics. Like, I don't know exactly how, but like I do think that as we get better on like eavesdropping on cells, even with cancer, right? There's like
Yeah.
circulating tumor DNA that people can just get like pick up the
All my
remnants.
patients are doing that now. It's
Yeah.
amazing how many,
Yeah.
even since I started in this field to now, how many more patients are using these. They're like these startup companies where they
Yep.
can detect the tiniest amounts of DNA in their blood and see if their tumor markers are going up or down long before they see anything on
And so
scans.
yeah, for people that are listening that might not know what circulating tumor DNA, like tumor cell DNA is about, it's like it's like not necessarily you're not going for a biopsy into the tumor. You're just picking
Right.
up what they're spewing out into the blood when they die. So when cells die, they release their DNA, and you can just eavesdrop. It's like
Hmm.
almost like looking. Gosh, I sound like I don't do this, but like if you want to find out what's going on at your neighbor's house, you can look through their trash. They're just like spewing it out there.
Right. That's a good way to put it. Or like the environmental DNA research where people are like collecting, from an elephant footprint to see what ecologically is living in there, or like,
that's a
looking
much
for
more
endangered
beautiful
species.
thing than like looking through your neighbor's trash. But yes. So
they both work.
Yeah.
They both
So
work.
going back to what we were talking about, trying to trace this back to, we're talking about the brain. Oh yeah, I do think that like, and the thing about the brain is like oftentimes the things you're talking about, like sleep regulation, these are like very small clusters of neurons having this kind of like weights, like stuff. Like I'm so fascinated always with there's a theory about our weight is kind of, we have a set point in our brains that like tells our body like how much to weigh. And we're talking about like clusters of cells. Like we're not talking about like giant golf ball sizes of tissue. So it's hard. The reason I'm saying that is like, it's much harder to sample. I don't want someone going and biopsying these cells because they can't. It's too small a region. But maybe we could figure out a way to eavesdrop on what mutations are happening there, or do some imaging that's like informed by some mouse studies that show when you have mutations, there's a certain structural distinction. Like, who knows?
And precision medicine is like such an obvious outcome of this type of sampling, which we're seeing, kind of starting in research settings. Definitely like in the cancer world, we mentioned there are these I guess surveillance approaches that allow for the tiniest amount of genetic material to be found in the blood. But think about like psychiatry, for example. Like, why does Prozac work on me when like, I don't know, citalopram makes me feel like shit?
Right.
We might be able to figure that out later.
Like if I take Allegra, I'm like, probably I should be an Allegra sales. If anyone's from Allegra listening, I will be like your sales promoter or whatever. But if I take a Zyrtec or, like I'm just done. I can't function for weeks. And there's certain people that are like more sensitive to Zyrtec than, and so yes, I do hope that one day we'll be able to have more of like the pharmacogenetic insight. But I guess that strays a little far from my main message here, which is like, even if I'm not sensitive to something today, my immune system might change because of mutation and I might be sensitive to it tomorrow. So part of the thing I want to emphasize is like, we have to give ourselves grace. Like a lot of the time we're trying to figure out like who we are, like what our bodies are doing. And then all of a sudden, I don't know, you find out you're allergic to something, but you could eat it before. Like what's going on? Well, our bodies change. Like cells turn over, DNA changes. And my message is like, we got to kind of get our arms around that whole concept.
And so, this maps really well, I think, in a lot of ways to the research that we're constantly talking about on another podcast I work on, The Skeptic's Guide to the Universe. We cover different science stories every single week, and very often we'll be saying, based on the, whatever UK biobank data, new researchers have, gotten into this big database and they've learned that this is how many steps you want to walk a day, or they've learned that like this is how many vegetables, on average people would eat, and then it has this downstream effect on what we always are calling all-cause mortality, right? Because it's like the broadest way to measure. People who did this died, later than people who did that.
Yeah.
And so, what are those things that help me not die as soon? And obviously, when you drill into research like that, there are a million nuances and 1,000 variables. But it does make me wonder how much underlies, how much of this really is what's going on with our DNA, with all of these behavioral changes that have all-cause mortality effects downstream.
Yeah, and by the way, I was just gonna say, although I love me a good UK biobank study, you threw that out as the example. All roads lead back to this UK biobank, which of course is like UK like decided to get really serious about getting like DNA sequences from a bunch of people, and they're just like they've got a huge repository now. So it's But yeah, your question about like how much of variance in our fate is due to our DNA and also the DNA mutation that happens in us. And I think the answer is like a lot more than we have appreciated in the past. And like when I keep going back to that thing I mentioned about how like a single blood cell from a centenarian has 3,000 mutations that aren't found in other parts of the body. Like I just feel like we're going to be talking a lot more about how our behaviors do affect our mutational rates and like in different ways. So one thing I found out as I was wrapping up the book that I was able to include is that, so first of all, let me just back up and say we've gone from not understanding how much a person mutates in the course of their life. Like 15 years ago, 20 years ago, we didn't even talk about this, right? We've gone from like
Yeah.
basically not a lot of data or zero data to like too much data, like data that computers will have to crunch to make sense of. Because what happened is in 2009, scientists developed ways to get the genetic sequence from individual cells. So no longer were they kind of looking at the bulk DNA of the body and making like a general assumption about the DNA of a person. All of a sudden, you can do like a census and be like, well, these cells have this mutation in this person, but these cells don't have this mutation in this person. Like something happened at some point. Like that is all in the last decade, really, that labs have been able to adopt the technology. And so going back for a second, like just to say, as I was wrapping up the book, they had crunched all of this like almost noisy data, like it's almost noisy, it's so much, and found that there's actually a different DNA mutation signature in people who smoke tobacco versus chew tobacco. Like the people that chew tobacco have a different mutational pattern than those who smoke it. So like we are going to get more granular insights into how our behaviors affect our DNA. Like, and that is so profound to me. Like just to know that like what we choose to do. So it's kind of like adding a layer. Like you're talking about like, you have a bunch of people, you look at their DNA, you have all-cause mortality. Now I think we're going to have this extra layer that's like, okay, they have that baseline genome, but then they're doing these behaviors that these are the mutations they're finding, and that's linked to their mortality.
Yeah, and like here's the thing that I'm going to start getting a little like philosophical, psychological about this because again, I'm seeing this through my lens as a health psychologist in a large metropolitan cancer center. One of the biggest struggles that I have with my patients is the why me? What could I have done to prevent this? Is it because I didn't eat more vegetables? Is it because I wasn't, I didn't take that class that, would have kept me more active? And so much of the work that we are doing often is grappling with the randomness of cancer, the fact that cancer is not terribly selective, and that some people, like you mentioned before, it's a loaded term, but are just kind of like genetically unlucky. And I'm always worried about, while on the one hand, learning more about how our behaviors can affect these our DNA downstream, I think will be very empowering for making choices. I sometimes worry that it maps back to the sort of power of positive thinking movement, The Secret, all of this, like, well, you manifested this because of some of the choices you made.
I'm already worried. Like or as I was writing about this DNA and cigarettes and tobacco and things like that, I was already worried about like the first paper linking microplastics to mutations, which is it's gonna come, right? And
100%.
All the thousands of TikToks that will launch. Like I do
Right.
think that like what you're saying is true, that there's a lot of danger here in, or this is walking a super fine line. There's a danger that we're going to try to be overly prescriptive in like behavioral change based on like very early studies linking certain behaviors to certain mutational patterns.
And judgmental, and also prey on people with a lot of pseudoscience.
Yeah. Well, it's a treacherous zone where you have a lot of people looking to say something about biology when it's got to be careful. At the same time, like it's funny because I actually wrote my book in part to address this why me question, because I did want to introduce the idea of randomness to people and for people to make peace with mutation. Like we should talk about how it's good for you because I think that's really important. But I'll also say that in the 2 decades I've been reporting on genetics, a lot of it has been on rare disease, families affected by like these genetic mutations that are rare. And I feel like there's an othering of people that have really obvious mutations. And I want to make I should make a shirt this summer that's like, I am a mutant, because we're all mutants.
Mhm.
And I think that part of what I'm trying to do is just get people to accept that, like, to live is to mutate is to live. And so what I want to say about immunity is, like, if your immune cells don't mutate, you can't make antibodies to fight the pathogens you encounter in your life. The engine of our immune system is mutation. So I don't know if you want to talk about that, but that's a super important flip side of all the negative things we've been talking about.
Yeah, I think that 100% that segue is necessary, especially right now, because the way I plan to get into it, which, God, it just makes me realize how old I am and how long it's been since I actually did recently finish my PhD, but how long it's been since I took a biology class, because that was in psychology. But I was going to bring up how, like, sickle cell, like, that's always the example, right? Like, sickle cell is like this horrific disease, and it can cause so much pain and so much disability for so many people, but it happens kind of as an outcome of good mutations that a lot of people are carrying that help prevent them from pretty debilitating malaria infections, right? So there's, like, often we do see like two sides of the same coin, even within similar genetic mutations. But what I'm hearing from you is that, like, we got to stop thinking about mutation as like putting a moral judgment on it anyway, or as somehow
I had a whole
bad.
debate. I mean, it's interesting that in my earlier question, you're like, oh, not to get philosophical. I'm like, this is all philosophical. Like, this is all, like, it's all philosophy. Like, it's not like just like hard science. Like, I really try to approach this topic through stories, like history, stories, patient narratives, and like, and really like the deeper philosophy of what all this means. So everybody here remembers the COVID pandemic, right? We all
No,
right?
when was that? Totally black that out.
So when our bodies had never seen COVID before, nobody on Earth, no human being on Earth had like encountered COVID before, and yet, despite the tremendous human loss, many of us got it. And our bodies could fight it off. How could they fight a disease they had never seen before? How could my immune system, and I'm assuming you got COVID, your immune system.
Yeah, 3 times. Yep.
Oh, man. I'm on 2, so better knock on some wood. So how could our bodies fight it? And the answer is, our immune cells have a weird function where their DNA can shift around and change a lot. And what they do is they kind of pull a lever. You never, like, the Vegas style, like, what they call slot machines, that you pull the lever and the things spin around, and then, like, you get different combinations. That's going on inside our immune cells all the time with our DNA. Just imagine the cell like pulling a lever. There's not like an actual lever, but just there's functions that switch around the DNA. And what happens is you get a different instruction from that sequence, and it makes an antibody with a different shape. And so it's just constantly making different mutations, hoping one will make an antibody that's necessary. It's just playing the odds, if you will. And so much so that, okay, well, anytime you get sick, it's like doing this process, right? But when you get a vaccine, it also does it. So these researchers in New York I write about looked at people who had gotten like a booster shot, which again further causes more mutation, hence like more benefit. Like, mutation is good in this instance. There are people that can't mutate their immune cells, and they have to live in like sterile bubbles or get transplants so that they can have like a reset of their immune system from somebody else that then gives them the ability to mutate. And so even people that got like these booster shots had immune cells that could make antibodies against versions of COVID that had not yet even existed, like those variants that had not yet come along, which was miraculous, if you ask me. So that's a good side of mutation. I don't know if I explained it well.
Absolutely. I mean, it's a weird moralization that we do from a scientific perspective. I think because we are the center of our own universe, and when we think about biological processes. Very often we think of them from a sort of anthropocentric perspective. So we're like, does it make me sick? Does it let me feel good in my body?
The sickness is easier to see, though, also. Like, I think some of the
Right.
meaning we give the term is because, like, there's mutations that every time we have a drink, like, of alcohol, like, our livers are getting insulted, the scientists say, the doctors say insulted. I mean, it's a nice way of putting it, maybe. And they've found evidence that, like, even in healthy people, when livers get damaged, when they're around, like, if you have too many calories, if you end up, like, going towards fatty liver disease, the immune cell, sorry, not the immune cells, the liver cells that regenerate in your liver oftentimes pick up mutations that help them process extra calories better, like sequester the extra ones they don't need better. So, so there's, and like, we would never know that's going on until this age of DNA sequencing. So some of this stuff's been, like, the good side of mutation's been hidden. We just take it for granted. And, and I do think that maybe part of it's also that we're not super comfortable with change. We're like, this is my body. Like, I don't need the DNA to change, but sometimes it helps us.
Well, and I think it's also why there's this ever difficult struggle, and I wish somebody would tell this to all of the billionaire investors out there, but there's this sort of push-pull and this difficult struggle between, I don't want to say between because it makes it sound like it's diametric, and it's not. It's more complicated than that, but between sort of like aging research and anti-aging research and cancer research. Like, the very things that we could do sometimes to our bodies to make us live longer could be very dangerous because they can, like, induce cancer in us and vice versa. And I think we're always, like, there's always this, like, oh, if we just, like, drink, this potion, or we just, change our cells so that they don't do this thing anymore, I'll just live forever. And I'm like, yeah, and you'll just be loaded with more mutations, and you'll have way more diseases you'll be fighting off the whole time.
Yeah, like, I don't have time. Like, I think if people really want to know the full story, they should read the book. But one of the things I'll mention is that, like, even antioxidants, it's like, I was like, oh, they must be great. But as I looked into it, it's like more, like, a little bit can be good, but, like, too much is actually linked to worse outcomes. So, it's like what your grandmothers all said about, like, moderation, so true, so necessary. And, like, it is also interesting because not just cancer that, like, anti-aging stuff doesn't just necessarily increase risk of cancer. It also, like, if you think about it, because there are companies now starting up that I write about that are trying to, like, slow mutation from happening in the body on the premise that, like, mutation is what causes frailty and aging and all these things. But of course, as we just talked about, like, if you can't mutate, you're not going to make new, better antibodies. So is the compromise of slowing mutation going to be a weakened immune system? TBD. I'm not going to try it out.
It's such an important point. We talk about this a lot on the SGU, kind of going back to the overarching point that, you see all of this pseudoscientific bullshit online about, like, we want to boost your immune system. Well, that's good to a point until it becomes, until you get an autoimmune disease, right? And, like, you want to you want to take these antioxidants or, like, reduce oxidative stress. Well, that's good to a point until, and everything is like that. Like, everything is toxic and large enough or small enough, depending quantities or lack thereof.
Like, going back to the immune system again, not that I'm hung up on it, but I did write a lot about COVID. During the pandemic, a lot of discussion on Twitter was about how to boost your immune system. And there was a lot of people saying, like, oh, the vaccines, like, it's like 5G, gonna, like, change your DNA. And of course, like, the mRNA vaccines do not directly change your DNA. Like, nothing is getting inserted into your DNA. Like, let's just be absolutely clear about that. But you do need, like, it is going to mutate. It's going to cause mutational processes in your DNA to make better antibodies. So instead of saying, like, I would say a strong immune system is a diversified one. And that diversification is really helped by vaccines. Like, if you're not taking vaccines, you're not diversifying your immune system. So it's not going to be as ready to, like, it doesn't have that antibody it needs in place at the get-go. You're going to be trying to make it on the fly, and, like, good luck. because you might not
Yeah.
make it in time.
It's why I always get my flu shot every year, even if it turns out that it's not that effective that year. My assumption is if I'm doing it every single year, I am developing immunity to all these different strains of flu.
I need to be very clear that I was vaccine hesitant, and I'm a reporter for 20 years on, I did not get the flu vaccine, despite the fact that I was living with somebody. He would always get the flu vaccine, and I'd be like, I don't need the flu vaccine.
So you were secondarily protected by him.
Maybe so.
Yeah.
But I got it one year, not that long ago, less than a decade ago. And about a month later, I had like a really mysterious lethargy. Went to 2 doctors, like couldn't figure it out. They tested me for CMV, which is like cytomegalovirus, because I had already had mono. Turns out I had subacute thyroiditis, and the only reason they found out was I was like really I was very tired, to the point where I was drinking maple syrup from like a glass, and eating double hamburgers and going to spin class like 6 times a week. It was like things were weird, and I was still very tired, and yet like jacked up in terms of like I was talking fast. So so finally I went to this like ear, nose, and throat doctor because I had like my neck was weird, and it was the kind of appointment you don't want to have, where the doctor walks into the room, looks at you, and then is like, yeah, I'll go get somebody else. And you're like, wait, don't you want to diagnose me? And he's like, no, I just diagnosed you. I just looked at you. So I had a lump on my thyroid, and it was because it was like it was like bursting. Now, why did I bring this story up? Because subacute thyroiditis is often a post-viral effect. So this is like, you lose your thyroid tissue. It's like not great. But if I had gotten the vaccine, I probably wouldn't have had as severe a flu, and I probably wouldn't have had. But then, like, who knows? Going back to like the whole thing we were talking about, like, why me? Maybe I would have still have had the mutation that would have precipitated that whole thing. So who knows?
We do what we can with the tools that we have available. And I feel like the responsible thing is to find balance in your life and to utilize the tools when they are when you have access, when you are in a privileged enough position to do them. I think where things get irresponsible, right, is where people have access to tools that are evidence-based, and they refuse to utilize those tools, not because of a legitimate risk, but because of an imagined or a agenda-driven description of risk that's not actually, based in science. That's when things are worrisome for me, living in a country where there are people at the helm and giving global health advice or national health advice who do not have the expertise that they need to be able to do that.
I was going to say the whole irony of the story, the long story I told you, is I was drinking maple syrup before I even lived in Canada, where I am now. So it would have been much cheaper to do here. And I have to apologize if my allergies are acting up. So if I'm like sniffling a bit, that's me in June, basically.
That's your DNA, man.
Well, allergy is probably linked to immune cells gone wrong. So anyway.
Probably everything. I mean, it's like whenever I talk on the show about patriarchy or I talk about intersectionality, and like, it's one of those things where you start, once you see it, you can't not see it everywhere. And I imagine
patriarchy is linked to mutation. And I was like, let me ponder that one a little bit more.
I'll figure out how it is. No, but like probably once you start thinking in terms of, like we started thinking in terms of cell turnover itself. Once we realized that your cells are not permanent, it changed the way we thought about biology. Now that we realize that your DNA is not permanent, that it's constantly changing throughout the lifespan, it probably does. It's the water that these researchers and these biomedical scientists, but also practitioners, are probably starting to swim in, and
it's changing.
It has explanatory value.
Everything. And like I feel so glad that I did this book, because now I'm like, well, I told you so. Like I said it, and during the pandemic, I was the first journalist to write about COVID being airborne, and I did it at a time where a lot of my friends who are science journalists were like, "Don't say that, Roxanne. Like, it's just wash your hands." And I was like, "No. I know these virologists. I know these." Aerobiologists, I think this is something I need to say. And I said it, And I felt so good after I said it, even though it took like 6 months for people to like, for Fauci to come along and be like, oh, actually also wear a mask. I don't know if it was 6 months, but it was several. It wasn't right away. But I feel the
Oh, yeah,
same
it
way
was.
about this. I feel the same way. I feel like I said it and now I can relax because I'll let other people kind of like catch up to it and like feel the consequence of it. But I do think it's a really important thing for people to grasp.
Well, gosh, speaking of relaxing, then I have to ask, are you back to your nonsense? Are you just finding really interesting stories within these fields and
Yeah,
continuing
totally.
to report on
Totally.
them? Do you have
Yeah.
any new obsessions that you're chasing down now?
I mean, interestingly, when I was writing this book, people were like, "Oh, so you're writing about epigenetics?" And I was like, "No, no, 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 no." Like, so epigenetics refers to like the markers, these chemical tags that end up on DNA to like turn it on or turn it off, but it doesn't
Mhm.
actually change the DNA sequence itself. And these tags can change through behavior. So like again, like going back to smoking or exercise or all these things, like it can modify like which genes are turned on and off by the addition or subtraction of these epigenetic tags. So I've gone back to actually writing about that, and I have a cool story coming up about that in Nature and Nature magazine. So yeah, like I'm back on my stuff, as you could say.
Amazing. I love it. Well, everybody, the book is Beyond Inheritance: Our Ever Mutating Cells and a New Understanding of Health. It's been such a pleasure to chat with you today. And there's so much in here that we did not get to. So, guys, pick up the book because I know you're going to love it. Thank you, thank you, thank you so much to Roxanne Khamsi. Thank you for being here. It was just a joy.
Tara, that was so much fun. I'm so glad we talked. Thank you.
Me too. And everybody listening, thank you for coming back week after week. I'm really looking forward to the next time we all get together to talk nerdy.